Welcome to Part 3 topic. Designing perimeter security. Perimeter security is the first protective boundary around your cloud environment. It is the layer that decides what traffic is allowed to reach your workloads and what must be stopped before it ever gets close to your applications or data. Before identities, permissions, or application logic come into play, perimeter security answers a simpler but critical question. Where is traffic coming from, and should it be allowed inside at all? To understand this, imagine your cloud environment as a secured campus. The buildings inside may have their own locks and access controls, but the outer gates still matter. If the gates are wide open, attackers can roam freely and probe every door. If the gates are carefully controlled, only expected and trusted traffic can even attempt to enter. That outer gate is what perimeter security represents in Google Cloud. In Google Cloud, perimeter security is built primarily around networks. Your workloads live inside virtual private cloud networks, commonly called VPCs. A VPC is not just a collection of IP addresses. It is a logical security boundary. Every virtual machine, load balancer, or managed service connected to that VPC inherits the protections you define at the network level. Traditional data centers relied on physical firewalls placed between internal networks and the internet. Cloud environments work differently. In Google Cloud, firewalls are software-defined and distributed by design. There is no single choke point where traffic passes through a hardware appliance. Instead, firewall rules are enforced close to the workload itself, across Google's global network. This approach improves performance and resilience while still providing strong security controls. At the heart of perimeter security are firewall rules. Firewall rules determine which network traffic is allowed or denied based on direction, source, destination, protocol, and port. Direction matters because traffic can either enter your network or leave it. Inbound traffic is controlled using ingress rules, while outbound traffic is controlled using egress rules. Thinking in terms of direction helps you design clear and predictable security boundaries. Ingress rules protect your workloads from unwanted external access. They decide which sources are allowed to initiate connections into your VPC. Without carefully designed ingress rules, any system exposed to the internet becomes a potential attack target. By restricting sources to known IP ranges, internal networks, or trusted services, you drastically reduce the attack surface. Egress rules are equally important, but often overlooked. They control where your workloads are allowed to send traffic. This is critical for preventing data exfiltration and limiting the impact of a compromised system. If an attacker gains control of a virtual machine, strong egress rules can prevent that system from freely communicating with external command and control servers. Another key concept in perimeter security is targeting. Firewall rules in Google Cloud do not apply randomly. They are associated with specific virtual machines using network tags or service accounts. This allows you to apply different security rules to different types of workloads, even when they share the same network. For example, a public-facing web server and an internal database can coexist in the same VPC while being protected by very different firewall policies. Perimeter security is not just about blocking traffic. It is also about visibility. Firewall logging allows you to see which rules are being matched and what traffic is being allowed or denied. These logs become invaluable during investigations, audits, and security reviews. They help confirm that your rules behave as intended and provide early warning signs of suspicious activity. Beyond basic firewall rules, perimeter security also includes higher-level protections. Load balancers act as controlled entry points to your applications, absorbing traffic and exposing only what is necessary. Web application firewalls add another layer by inspecting HTTP and HTTPS requests for common attack patterns, such as SQL injection or cross-site scripting. These controls focus on application-level threats rather than just network-level traffic. Perimeter design also involves making careful decisions about public and private access. Not every workload needs to be reachable from the internet. Many services should remain private, accessible only from internal networks or trusted environments. By limiting public exposure and using private connectivity wherever possible, you significantly reduce risk. Ultimately, designing perimeter security is about balance. You want to allow legitimate users and services to access what they need, while making it as difficult as possible for attackers to reach anything of value. Strong perimeter security does not rely on a single rule or product. It combines layered controls, clear network boundaries, and thoughtful access design. When done correctly, perimeter security becomes an invisible guardian. It quietly filters traffic, enforces boundaries, and absorbs attacks, giving your applications the space they need to operate safely. It is not the only layer of defense, but it is the first one an attacker must face, and often the most important one to get right. Topic: Configuring network perimeter controls. In this section, we focus on how network perimeter controls are designed and configured in Google Cloud, and why they are such a critical part of cloud security. For decades, firewalls have been the primary mechanism used to protect networks. Their purpose has always been simple in concept, but powerful in effect. They decide which traffic is allowed to enter a network and which traffic is allowed to leave. Every request that crosses a network boundary is evaluated, and only traffic that matches defined rules is permitted. In traditional environments, firewalls usually exist as physical or appliance-based systems. Some are placed at the edge of a network, sitting between an internal local network and the wider internet. Others are installed directly on individual machines, controlling traffic at the host level. These approaches work, but they also introduce limitations. Physical firewalls can become bottlenecks, and scaling them to handle increased traffic often requires additional hardware and complex redesigns. In Google Cloud, network perimeter controls take a very different approach. Firewalls are not physical devices at all. They are software-defined constructs that run on top of Google's global software-defined networking infrastructure. This design choice changes everything. Instead of traffic being forced through a single choke point, firewall enforcement is distributed across the entire network fabric. As traffic grows, the firewall scales automatically, without introducing performance bottlenecks. At the heart of network perimeter protection in Google Cloud is the Virtual Private Cloud, or VPC. Every VPC network has an implicit firewall that denies all incoming traffic by default. This means that, unless you explicitly allow traffic, nothing from outside the network can reach your resources. From a security perspective, this default deny behavior is a strong starting point. To allow legitimate communication, you define firewall rules. These rules describe exactly what kind of traffic is permitted or denied. They apply at the VPC level and are enforced consistently across all resources attached to that network. Because the rules are global to the VPC, you do not need to configure firewalls individually on every virtual machine. When a firewall rule is evaluated, Google Cloud looks at several characteristics of the traffic. It considers where the traffic is coming from, where it is going, which protocol it uses, and which ports are involved. Based on these attributes, the rule either allows the traffic to pass or blocks it. Firewall rules can apply to incoming traffic, known as ingress, or outgoing traffic, known as egress. Ingress rules control what can enter your network from external or internal sources. Egress rules control what resources inside your network are allowed to communicate with destinations outside the network. This distinction is important because controlling outbound traffic is just as critical as controlling inbound traffic, especially when trying to prevent data exfiltration. Another key concept in Google Cloud firewalls is targeting. Firewall rules do not have to apply to every resource in a VPC. Instead, you can scope them to specific workloads. This can be done by targeting network tags or service accounts. Network tags let you group virtual machines based on their role, such as web servers or database servers. Service accounts let you tie network access directly to the identity used by a workload. This gives you fine-grained control and aligns well with the principle of least privilege. Rule priority also plays a major role. When multiple firewall rules could apply to the same traffic, Google Cloud evaluates them in order of priority. Rules with a higher priority are evaluated first. As soon as a matching rule is found, its action is applied, and no further rules are considered. This makes it possible to define broad default rules while still enforcing strict exceptions where needed. Because these firewall rules are distributed and software-defined, they operate invisibly in the background. There is no single device to manage, no hardware to scale, and no performance bottleneck to worry about. From the perspective of your workloads, traffic is either allowed or denied seamlessly. In summary, configuring network perimeter controls in Google Cloud means defining clear, precise firewall rules at the VPC level. These rules establish the first line of defense around your workloads. They control how traffic enters and leaves your network. They scale automatically with demand, and they provide the foundation for more advanced security controls that build on top of the network perimeter. Topic: Configuring firewall. Rules. Imagine your cloud network as a secured facility with guarded entry and exit points. In Google Cloud, firewall rules are those guards. They decide exactly which traffic is allowed to enter your virtual private cloud and which traffic is allowed to leave it. Every VPC network in Google Cloud starts with a strong default stance. Incoming traffic from outside, the network is blocked automatically. Nothing gets in unless you explicitly allow it. This design mirrors the idea of a traditional data center demilitarized zone, but with one major difference. Instead of a single physical firewall sitting at the edge, Google Cloud firewalls are software-defined and globally distributed. There is no single bottleneck. Protection scales automatically with your traffic. A firewall rule is simply a clear statement of intent. It says what kind of traffic you allow or deny, where that traffic comes from or goes to, and which virtual machines the rule applies to. These rules always belong to a VPC as a whole, not to individual subnets or specific machines. The enforcement happens everywhere, at the network fabric level. When traffic flows into your VPC, it is evaluated by ingress rules. These rules control traffic coming from a source outside or inside the network toward your virtual machines. When traffic flows out of your VPC, it is evaluated by egress rules. These rules control where your workloads are allowed to send data. If you do not specify a direction, Google Cloud assumes ingress by default. Each firewall rule has a priority, and priority matters. Rules are evaluated in order, starting from the lowest number, which represents the highest priority. The first rule that matches the traffic decides the outcome. This makes rule ordering critical. A broad allow rule placed above a restrictive deny rule can accidentally open access you never intended. You also decide whether a rule allows traffic or denies it. This simple choice becomes powerful when combined with precise targeting. In Google Cloud, firewall rules do not apply blindly to every virtual machine. Instead, you define targets. A target is the set of instances the rule applies to. You can target all instances in the VPC, or you can narrow the scope using network tags or service accounts. Network tags are labels you attach to virtual machines. When a firewall rule targets a tag, only instances with that tag are affected. This is useful, but it comes with responsibility. Tags themselves have no built-in access control. Anyone who can modify an instance could attach a tag and inherit the rule's permissions. Service accounts provide a stronger alternative. A service account is both an identity and a resource, protected by IAM. When you target firewall rules using service accounts, Google Cloud enforces identity checks behind the scenes. Only workloads that are explicitly allowed to use that service account can be affected by the rule. For sensitive workloads, this adds an extra layer of defense. Every firewall rule also defines protocols and ports. You can allow or deny specific protocols like TCP, UDP, or ICMP, and you can restrict traffic to exact ports or ranges of ports. If you do not specify protocols and ports, the rule applies to all traffic, which is rarely what you want in a secure environment. For ingress rules, you define sources. These can be IP ranges, tagged instances, or service accounts. For egress rules, you define destinations, usually as IP ranges. This distinction is important. Ingress rules never use destinations, and egress rules never use sources. Remembering this helps avoid configuration errors, especially during the exam. Firewall rules are enforced automatically as soon as they are created, unless you explicitly disable them. This allows you to stage rules in a disabled state for testing or review before enforcement. Visibility is just as important as control. Firewall rules logging allows you to record every connection that is allowed or denied by a specific rule. When logging is enabled, each connection generates a detailed record showing source and destination addresses, protocols, ports, timestamps, and the rule that made the decision. These logs are sent to cloud logging and can be exported for deeper analysis. This makes firewall rules not just a security control, but also an auditing and investigation tool. Taken together, firewall rules form the first line of defense at the network perimeter. They are global, scalable, identity-aware, and precise. When designed carefully, they ensure that only the right traffic reaches your workloads and that any unexpected behavior is quickly visible. In Google Cloud Security, this is where network protection truly begins. Target network tags and service accounts in cloud networking. Not every control lives at the edge of the network. Some of the most powerful protections operate much closer to the workload itself. This is where target network tags and service accounts come into play. Imagine a cloud environment where hundreds of virtual machines are running different workloads. Some serve web traffic, some process background jobs, and others handle sensitive internal operations. Treating all of these machines the same from a network perspective would be risky. Instead, Google Cloud allows you to define exactly which workloads a firewall rule should apply to, and it does this through target network tags and service accounts. Target network tags are simple labels that you attach to virtual machine instances. These tags do not change how the machine behaves on their own. Their real power comes from how firewall rules use them. A firewall rule can be written to apply only to instances that have a specific tag. For example, only machines tagged as web server may be allowed to receive traffic on port 443 from the internet. Any machine without that tag is automatically excluded, even if it exists in the same network. This creates a clear separation of responsibilities without needing separate networks for every workload. Service accounts take this idea a step further. Instead of identifying machines by a label, service accounts identify them by identity. Every virtual machine can run as a specific service account, which represents who that workload is, not just what it is called. Firewall rules can target these service accounts directly. This means access decisions are tied to identity rather than configuration labels that might be reused or mistyped. This identity-based approach is especially useful in dynamic environments. Instances may be created and destroyed automatically by auto-scaling groups. Network tags require careful consistency to ensure every instance is tagged correctly. Service accounts, on the other hand, are usually baked into the workload design. When a new instance starts, it automatically carries the correct identity, and the firewall rules apply immediately without manual tagging. Using target network tags and service accounts helps shrink the attack surface. Instead of opening access broadly across a network, rules can be narrowly scoped to only the workloads that truly need it. If a single virtual machine is compromised, the attacker does not gain unrestricted network access to other systems. The damage remains contained. In practice, network tags are often used for simple, role-based grouping, while service accounts are preferred for stronger, identity-driven security models. Together, they provide precise control over how traffic flows inside and into your cloud environment, forming a critical layer of your network perimeter defenses. Priority in cloud security. Not every rule is equal. Some rules must take precedence over others. And this is where priority becomes critical when configuring network perimeter controls. Priority defines the order in which security rules are evaluated when traffic attempts to enter or move within your environment. Every incoming request is checked against these rules one by one. The moment a rule matches, a decision is made, and no further rules are evaluated. This means that the position of a rule can completely change the outcome, even if multiple rules seem correct on paper. Imagine a guarded facility with multiple security checkpoints. If a guard at the outer gate allows someone through without checking their credentials properly, it no longer matters how strict the inner checkpoints are. The same logic applies to network perimeter controls. A high-priority rule that is too permissive can override stricter rules placed below it, unintentionally opening access to sensitive systems. Google Cloud, priority values are usually numerical, where lower numbers represent higher priority. A rule with a priority of 1,000 is evaluated before a rule with a priority of 2,000. This simple ordering mechanism becomes powerful when used correctly and dangerous when misunderstood. High-priority rules should be reserved for the most critical decisions. These often include explicit deny rules that block known risky traffic or restrict access from untrusted networks. By placing these rules at the top, you ensure that dangerous traffic is stopped immediately, before any broader allow rules can take effect. Lower priority rules are typically more general. They might allow routine access for applications, internal services, or trusted users. These rules only come into play after the system has confirmed that no higher priority restrictions apply. This layered approach helps maintain both security and functionality. Poorly managed priorities can lead to silent security gaps. A common mistake is adding a new allow rule without realizing it has a higher priority than an existing deny rule. On the surface, everything appears configured correctly, but in reality, the network is now exposed. These issues are especially dangerous because they often go unnoticed until an incident occurs. Effective use of priority requires careful planning. Each rule should have a clear purpose, and its priority should reflect how critical that decision is to your security posture. Rules should be reviewed regularly, especially as environments grow and change. What made sense during initial deployment may no longer be appropriate months later. When used properly, priority transforms network perimeter controls from a simple list of rules into a deliberate security strategy. It ensures that the most important protections are applied first, risks are contained early, and access is granted only when all critical checks have been satisfied. In cloud security, this order of evaluation is not just a technical detail. It is a foundational element of defense. Topic protocols and ports. Every conversation between systems on a network happens through rules. Those rules are defined by protocols and ports. To understand network perimeter controls, it helps to picture your cloud network as a secured facility. The perimeter is the gate around that facility. Protocols decide the language that visitors must speak. Ports decide which doors are open and which stay locked. A protocol is simply a set of rules that define how data is sent, received, and understood. When one system talks to another, both sides must agree on the protocol, otherwise the communication fails. In cloud environments, common protocols include TCP, UDP, ICMP, HTTP, HTTPS, SSH, and others. Each protocol has a purpose, and each one carries a different level of risk. TCP is the most widely used protocol for reliable communication. It ensures data arrives in the correct order and retransmits lost packets. Most business-critical applications rely on TCP because accuracy matters more than speed. UDP, on the other hand, favors speed over reliability. It sends data without checking if it arrived safely, which makes it suitable for streaming, voice, and real-time services, but also harder to control from a security perspective. Some protocols are designed specifically for diagnostics and management. ICMP, for example, is used for network testing, such as ping requests. While useful for troubleshooting, unrestricted ICMP can reveal valuable information to attackers about your network layout. That is why perimeter controls often restrict or limit its use. On top of these transport-level protocols, application protocols come into play. HTTP and HTTPS define how web traffic flows. HTTP sends data in plain text, making it easy to intercept and read. HTTPS adds encryption, protecting the data as it travels across the network. From a security standpoint, HTTPS is almost always preferred, and plain HTTP should be tightly restricted or blocked entirely unless there is a strong, controlled reason to allow it. Ports work alongside protocols to direct traffic to the correct service. A port is a numbered endpoint on a system where an application listens for incoming connections. For example, web servers typically listen on port 80 for HTTP, and port 443 for HTTPS SSH commonly listens on port 22, and databases often use their own specific ports. Every open port is a potential entry point. If a port is open, it means something is listening behind it. If something is listening, it can potentially be targeted. This is why network perimeter controls focus heavily on limiting which ports are exposed and to whom. A secure perimeter follows a simple rule. Deny by default, allow only what is necessary. Instead of opening wide ranges of ports, access is granted narrowly and intentionally. If an application only needs HTTPS access, then only TCP port 443 should be allowed. All other ports remain closed, reducing the available attack surface. Protocols and ports are also tied closely to identity and workload behavior. Not every system needs to talk to every other system. A backend service might only need to communicate with a database over a single port. There is no reason for it to accept inbound traffic from the public internet or to allow unused protocols. In cloud environments, these controls are enforced through firewall rules, security policies, and network boundaries. These rules evaluate traffic based on protocol, port, source, destination, and direction. Only traffic that matches an explicit rule is allowed to pass through the perimeter. Misconfigured protocols and ports are one of the most common causes of security incidents. An accidentally exposed management port or an unused protocol left open can become an easy target. Attackers often scan networks looking for exactly these mistakes. By carefully selecting which protocols are allowed and tightly controlling which ports are open, you shape the behavior of your network at its edges. You decide who can talk, how they can talk, and what they are allowed to say. This discipline turns the network perimeter from a weak boundary into a strong, deliberate line of defense. Topic: Direction. When we talk about configuring network perimeter controls, one of the most important ideas to understand is direction. Direction simply means understanding which way traffic is allowed to flow in and out of your cloud resources and controlling that flow very deliberately. Every network interaction has a direction. Traffic can be inbound, meaning it is coming into a resource, or outbound, meaning it is leaving a resource. In cloud environments, security problems often happen not because a service exists, but because traffic is allowed to move in directions that were never intended. Directional control is about deciding, very clearly, who is allowed to talk to what, and from which side of the boundary. Think of your network perimeter as the walls of a secured building. Direction defines whether doors open inward, outward, or both. An inbound rule controls who is allowed to enter the building. An outbound rule controls who is allowed to leave and where they are allowed to go. If you only focus on inbound access and ignore outbound traffic, you leave a hidden exit open. An attacker who gains access to a system could freely send data out, connect to command and control servers, or move laterally to other services. Inbound direction controls are typically used to protect services from unauthorized access. This includes deciding which IP ranges, networks, or identities are allowed to initiate connections to your workloads. For example, a backend database may only need to accept traffic from an application server within the same project or VPC. Allowing inbound access from the public internet would expand the attack surface unnecessarily. Outbound direction controls are just as critical and often overlooked. Outbound rules define where a workload is allowed to send traffic. A virtual machine that only needs to talk to a specific API or internal service should not be allowed unrestricted internet access. By restricting outbound traffic, you reduce the risk of data exfiltration and make it much harder for compromised resources to communicate with external systems. Direction also plays a key role in zero trust and least privilege networking models. Instead of assuming that internal traffic is safe, you explicitly define allowed directions even within your own network. East-west traffic, which is traffic between services inside your environment, should be controlled as carefully as north-south traffic that flows in and out of the cloud. In practice, configuring direction means creating rules that are explicit rather than permissive. You decide which resources can initiate connections, which resources can receive them, and under what conditions. Default deny rules are often applied so that traffic is blocked unless it is explicitly allowed in the correct direction. This approach ensures that accidental exposure does not occur simply because a rule was missing. Direction-based controls also improve incident response. When traffic directions are tightly defined, abnormal behavior stands out immediately. If a service suddenly attempts to send outbound traffic to an unknown destination, or receives inbound requests it was never designed to handle, those actions can be detected and stopped quickly. Ultimately, controlling direction at the network perimeter is about intent. You are encoding the intended communication paths of your system into enforceable rules. By doing so, you reduce ambiguity, limit the blast radius of compromises, and ensure that your cloud environment behaves in a predictable and secure way, even when something goes wrong. Topic: firewall rules logs. When you configure network perimeter controls in Google Cloud, firewall rules act as the first line of defense, deciding which traffic is allowed to enter or leave your virtual network. But defining rules alone is not enough. To truly understand whether your network defenses are working as expected, you need visibility. This is where firewall rules logging becomes essential. Firewall rules logging allows you to observe, audit, and verify how your firewall rules behave in real conditions. Every time traffic matches a firewall rule, whether that traffic is allowed or denied, a record of that decision can be created. These records give you concrete evidence that your security controls are doing what you designed them to do. If you create a rule to block unwanted access, logging lets you confirm that the rule is actually stopping connections, rather than silently failing. In Google Cloud, firewall rules logging is configured at the individual firewall rule level. This means logging is not automatically enabled for all rules. Instead, you choose which rules are important enough to monitor closely. This selective approach gives you flexibility and helps control logging volume and cost. Any firewall rule, regardless of whether it allows or denies traffic, and regardless of whether it applies to ingress or egress traffic, can have logging enabled, with the exception of the default implied rules that exist in every VPC. Once logging is enabled for a firewall rule, Google Cloud generates what is known as a connection record each time that rule matches traffic. These connection records are not sampled. Every matching connection is captured. This is an important distinction because it means firewall rules logs provide a complete picture of rule activity, unlike some other network logging features that only collect samples of traffic. Each connection record contains valuable context. It includes the source and destination IP addresses involved in the connection, the network protocol and port numbers, the date and time when the connection occurred, and a reference to the exact firewall rule that handled the traffic. With this information, you can trace network behavior, identify unexpected access patterns, and correlate traffic with specific security rules. All firewall rules logs are sent to cloud logging, which becomes the central place to view, search, and analyze them. From there, logs can be filtered to focus on specific subnets, virtual machines, or traffic coming from certain locations. This makes firewall rules logging useful not only for security investigations, but also for troubleshooting connectivity issues and understanding normal traffic patterns. In environments that use shared VPC, it is important to understand where these logs are stored. Even though virtual machines may run in service projects, firewall rules belong to the host project that owns the network. As a result, firewall rules logs are written to the host project. Knowing this prevents confusion when you are searching for logs during an incident or audit. Firewall rules logging plays a critical role in validating perimeter security. It helps you answer simple but vital questions. Is a deny rule actually blocking unwanted traffic? How many connections are being affected by a specific rule? Are there unexpected sources attempting to reach sensitive resources? By providing clear, consistent visibility into firewall behavior, firewall rules logging transforms static security rules into observable, verifiable controls that you can trust. Topic: firewall rule summary. In any cloud environment, firewall rules are the front line of defense for your network. They decide what traffic is allowed to enter, what traffic is allowed to leave, and what traffic must be blocked entirely. A firewall rule summary is not just a technical list of settings. It is a clear picture of how your network is protected and how data is permitted to flow. At its core, a firewall rule defines a condition and an action. The condition describes the type of traffic, such as where it is coming from, where it is going, which protocol it uses, and which port it targets. The action defines what happens when traffic matches that condition. The traffic is either allowed or denied. Every packet that tries to move through your network is evaluated against these rules. Firewall rules are typically evaluated in a specific order. When traffic enters the network, the firewall checks each rule one by one until it finds a match. As soon as a matching rule is found, the action for that rule is applied, and the evaluation stops. This makes rule order extremely important. A broad rule placed too early can unintentionally allow or block traffic that should have been handled by a more specific rule later. A summary of firewall rules helps you understand the overall security posture of your network at a glance. It shows which networks or IP ranges are trusted, which services are exposed, and which directions traffic is allowed to flow. For example, you might clearly see that web traffic is allowed from the internet to a public application, while administrative access is restricted to a small set of internal IP addresses. Firewall rules can be ingress or egress. Ingress rules control incoming traffic, deciding who can reach your resources. Egress rules control outgoing traffic, deciding where your resources are allowed to connect. Both are equally important. Allowing unrestricted egress can enable compromised systems to communicate freely with external attackers, while strict egress rules can significantly reduce the impact of a security incident. Another important aspect visible in a firewall rule summary is the principle of least privilege. Well-designed firewall rules allow only the traffic that is absolutely necessary. If an application only needs to communicate on a single port, only that port should be open. If a service is internal, it should not be reachable from the public internet. The summary helps identify overly permissive rules that increase risk. Firewall rule summaries are also essential for audits and troubleshooting. When something stops working, the summary can quickly reveal whether traffic is being blocked. During security reviews, it provides evidence that access is intentionally controlled and documented, rather than being the result of ad hoc decisions. Over time, firewall rules tend to grow and become complex. Old rules may remain long after the systems they were created for are gone. A clear summary makes it easier to identify unused or redundant rules and clean them up. This reduces confusion, improves performance, and strengthens security. In simple terms, a firewall rule summary tells the story of your network's boundaries. It shows who is allowed in, who is allowed out, and under what conditions. By regularly reviewing and understanding this summary, you maintain control over your network perimeter and ensure that your cloud environment remains secure, predictable, and resilient. Topic: configuring hierarchical firewall rules in a large cloud environment. Networks are rarely simple or flat. They grow over time, span multiple projects, and serve many teams with different responsibilities. As this complexity increases, controlling who can talk to whom on the network becomes one of the most critical security tasks. This is where network perimeter controls come into play, and within them, hierarchical firewall rules play a key role. To understand hierarchical firewall rules, it helps to first think about how organizations are structured in Google Cloud. Resources are organized in a hierarchy that starts at the organization level, then flows down to folders, and finally to individual projects. Each level of this hierarchy represents a scope of control. What makes hierarchical firewall rules powerful is that they follow this same structure. Instead of defining firewall rules separately in every single project, you can define rules at higher levels and have them automatically apply to everything below. At a basic level, firewall rules control network traffic. They decide which connections are allowed and which are denied, based on factors such as source address, destination address, protocol, and port. Traditional firewall rules are defined at the VPC network level inside a project. While this works well for small environments, it becomes difficult to manage consistently when you have dozens or hundreds of projects. Small differences between rules can introduce security gaps, and maintaining alignment becomes a constant challenge. Hierarchical firewall rules solve this problem by allowing you to define centralized, enforced network policies. When a rule is created at the organization or folder level, it applies to all VPC networks in all projects under that scope. This ensures that critical security controls are always present, no matter how many projects are created or who creates them. From a security perspective, this is essential for maintaining a strong and predictable perimeter. One important concept in hierarchical firewall rules is the idea of policy intent. These rules are typically used to enforce high-level security requirements rather than application-specific networking needs. For example, an organization may decide that no workload should ever accept inbound traffic directly from the public internet, or that management access such as SSH or RDP must only come from a controlled corporate IP range. By defining these rules hierarchically, you enforce these decisions everywhere by default. Another key aspect is rule precedence. Hierarchical firewall rules are evaluated before project-level firewall rules. This means they can act as guardrails. Even if a project owner accidentally or intentionally creates a permissive firewall rule at the project level, a higher-level hierarchical rule can still block unwanted traffic. This design helps prevent configuration drift and reduces the risk of human error leading to a security incident. Hierarchical firewall rules can be either allow rules or deny rules, but in practice, deny rules are especially powerful. Deny rules defined at a high level are difficult to bypass, making them ideal for blocking known bad traffic patterns or enforcing strict perimeter boundaries. Allow rules are typically used to explicitly permit required traffic paths that would otherwise be blocked by broader restrictions. These rules also support the concept of direction. Ingress rules control incoming traffic to resources, while egress rules control outbound traffic leaving them. Egress control is often overlooked, but it is a crucial part of a strong security posture. By using hierarchical egress firewall rules, an organization can prevent workloads from freely communicating with the internet or with unauthorized internal networks, reducing the risk of data exfiltration and command and control communication if a system is compromised. From an operational perspective, hierarchical firewall rules simplify governance. Security teams can define and maintain core network security policies in one place, while application teams remain free to manage their own project-level rules within those boundaries. This separation of responsibility aligns well with the principle of least privilege and reduces friction between teams. It is also important to understand that hierarchical firewall rules are not meant to replace all project-level firewall rules. Instead, they form a layered defense. High-level rules establish non-negotiable security requirements, while lower-level rules handle application-specific needs. Together, they create a consistent and scalable approach to network security. In essence, configuring hierarchical firewall rules is about shifting from reactive, project-by-project network control to proactive, organization-wide enforcement. By defining clear network boundaries at higher levels of the resource hierarchy, you reduce risk, improve consistency, and make your cloud environment easier to secure as it grows. Configuring load balancers. Load balancing is one of the foundational building blocks for protecting applications at the network perimeter in Google Cloud. At its core, load balancing is not only about distributing traffic. It is about ensuring that applications remain available, responsive, resilient, and secure, even under heavy load or during an attack. When users access an application, they do not connect directly to virtual machines, containers, or serverless services. Instead, their traffic first reaches a load balancer. This load balancer becomes the controlled entry point into your environment. From a security perspective, this is extremely important because it creates a clear boundary where traffic can be inspected, filtered, and managed before it ever reaches your workloads. Google Cloud load balancers are built on the same global infrastructure that powers services like Google Search, Gmail, and YouTube. This means traffic is absorbed and handled close to the user, across Google's global edge network. By doing this, Google can terminate connections, mitigate large traffic spikes, and reduce latency long before requests touch your backend services. In Google Cloud, load balancers come in different forms, but they can broadly be understood by two characteristics. The first is scope, which can be global or regional. A global load balancer can distribute traffic across multiple regions, while a regional load balancer keeps all components within a single region. The second characteristic is exposure. External load balancers accept traffic from the internet, while internal load balancers are designed only for private, internal traffic within your network. From a perimeter security standpoint, external load balancers are especially important because they sit directly on the internet-facing edge of your environment. Since they accept traffic from anywhere, they are also the primary target for denial-of-service attacks and malicious requests. To address this, Google Cloud integrates load balancers tightly with additional security services. One of the most critical integrations is with Google Cloud Armor. Cloud Armor provides an application layer defense that works alongside certain external load balancers. Incoming requests are evaluated before they are forwarded to backend services. This allows you to block malicious IP addresses, enforce geographic restrictions, and protect applications from common web attacks. In effect, the load balancer becomes a security enforcement point, not just a traffic distributor. Another important aspect of configuring load balancers securely is understanding what sits behind them. Backends can be virtual machine instance groups, network endpoint groups, serverless services like Cloud Run or App Engine, or even cloud storage buckets. The load balancer ensures that these backends are not directly exposed to the internet. Instead, they only receive traffic that has already passed through the load balancer's controls. Load balancers also play a key role in protecting against distributed denial-of-service attacks. Because traffic is terminated at Google's edge, large attack volumes are absorbed by Google's infrastructure rather than overwhelming your application. This protection is built in, but it becomes significantly stronger when combined with services like Cloud Armor, and for web applications, Identity-Aware Proxy. When you configure a load balancer, you are effectively defining how traffic enters your environment, how it is distributed, and what protections are applied along the way. This makes load balancers a critical part of the network perimeter. They enforce separation between the public internet and your private resources, reduce direct exposure of workloads, and provide a natural control point for layered security. In a defense in-depth model, load balancers are not the only security control, but they are often the first line of defense. By carefully configuring them, choosing the right type for your workload, and integrating them with security services, you create a strong and scalable perimeter that protects applications without sacrificing performance or availability. Configuring certificate authority. Service certificate authority service plays a quiet but critical role in securing communication inside a cloud environment. It is the system that issues, manages, and protects digital certificates, which are the foundation of trust between services, users, and devices. In a cloud network, services constantly talk to each other. Applications connect to databases, microservices exchange data, APIs respond to requests. Each of these interactions needs a way to confirm identity and encrypt traffic so that no one else can listen in or impersonate a trusted system. This is where certificates come in. A certificate is a digital identity card. It proves who a service is and allows encrypted communication using TLS without a trusted authority issuing these certificates. Secure communication at scale would be impossible. Configuring certificate authority service begins with understanding trust boundaries. Instead of relying on external or manually managed certificate authorities, organizations can use a private certificate authority inside Google Cloud. This gives full control over who can request certificates, how long those certificates are valid, and how they are rotated or revoked. The first step is creating a certificate authority pool. Think of this pool as a controlled factory for certificates. It defines where certificates come from and what rules they must follow. Within this pool, one or more certificate authorities can exist, typically starting with a root or subordinate authority depending on the security design. A root certificate authority represents the highest level of trust. Because it can sign other authorities, it must be protected carefully and used sparingly. In most real-world environments, a subordinate certificate authority is used for daily operations. This limits risk and helps contain damage if a key is ever compromised. Once the authority is created, policies define how certificates are issued. These policies control key sizes, cryptographic algorithms, certificate lifetimes, and allowed identities. This ensures that all certificates meet organizational security standards without relying on human judgment each time. Access control is a core part of the configuration. Only approved identities, such as specific service accounts or workloads, are allowed to request certificates. This prevents unauthorized systems from obtaining trusted credentials. IAM policies are used to enforce who can create, manage, or use certificate authorities. After access is defined, certificate issuance can be automated. Services can request certificates programmatically and receive them without manual intervention. This automation is essential in modern environments where workloads scale up and down constantly. Short-lived certificates can be issued and rotated automatically, reducing the impact of leaked credentials. Certificate Authority Service also integrates with network perimeter controls. Certificates can be used for mutual TLS, where both sides of a connection authenticate each other. This ensures that only trusted services can communicate, even if they exist inside the same network. If a service does not have a valid certificate, the connection is rejected. Monitoring and lifecycle management complete the configuration. Certificates are tracked, expiration dates are monitored, and revocation is available when needed. If a service is decommissioned or compromised, its certificates can be invalidated immediately, cutting off access. By configuring Certificate Authority Service properly, trust becomes centralized, automated, and enforceable. Encrypted communication is no longer optional or inconsistent. It becomes the default behavior across the entire cloud environment. In doing so, the network perimeter is strengthened not by firewalls alone, but by cryptographic trust that follows every workload wherever it runs. Identifying differences between private and public addressing in cloud networking. One of the most important security decisions you make is whether a resource should use a private address or a public address. This choice directly affects how that resource can be reached, who can see it, and how exposed it is to potential attacks. A public IP address is designed to be reachable from the internet. When a virtual machine, load balancer, or service is assigned a public address, it becomes visible beyond the boundaries of your cloud environment. Any system on the internet can attempt to connect to it, as long as network rules allow the traffic. This is useful for services that must be accessed by users worldwide, such as public websites, APIs, or internet-facing applications. However, this visibility comes with risk. A public address increases the attack surface because it invites scanning, probing, and direct connection attempts from unknown sources. A private IP address, on the other hand, exists only within a controlled network boundary. In Google Cloud, private addresses are used inside virtual private cloud networks. Resources with private addresses can communicate with each other internally, but they cannot be reached directly from the internet. This isolation is intentional. It creates a natural security barrier, ensuring that internal systems such as databases, backend services, and internal processing workloads are hidden from external traffic. The key difference is reachability. Public addressing allows global access, while private addressing limits access to trusted networks and approved pathways. From a security perspective, private addressing is always preferred unless there is a clear and justified need for public exposure. By keeping resources private, you reduce the number of entry points an attacker can target. Private addressing also plays a critical role in enforcing network perimeter controls. When systems are private, access must flow through controlled mechanisms such as load balancers, bastion hosts, VPN connections, or private service endpoints. These gateways act as checkpoints where traffic can be inspected, filtered, logged, and restricted. This design ensures that even if an attacker is on the internet, they cannot directly reach sensitive workloads. Public addressing should be treated as an exception, not the default. When it is required, it must be paired with strong controls such as firewall rules, identity-aware access, and continuous monitoring. Simply assigning a public IP without proper safeguards can expose critical systems to unnecessary risk. Understanding the difference between private and public addressing helps you design secure network perimeters. By keeping internal resources private and exposing only what is absolutely necessary, you minimize your attack surface, improve control over traffic flow, and strengthen the overall security posture of your cloud environment. Configuring web application firewall. Cloud Armor. Web applications are one of the most common entry points for attackers in the cloud. They are exposed to the public internet, constantly receiving traffic from unknown users, automated bots, and sometimes malicious actors. Because of this exposure, protecting web applications requires a strong defensive layer placed directly at the network perimeter. This is where a web application firewall, or WAF, becomes essential. In Google Cloud, this role is fulfilled by Cloud Armor. Cloud Armor acts as a protective shield in front of your applications, inspecting incoming requests before they ever reach your backend services. Instead of allowing all traffic by default, Cloud Armor evaluates each request and decides whether it should be allowed, denied, or challenged. At its core, Cloud Armor works by applying security policies. A security policy is a collection of rules that define what kind of traffic is acceptable and what is not. These rules can be based on many factors, such as the source IP address, geographic location, HTTP headers, request paths, or request methods. When a request arrives, Cloud Armor evaluates it against these rules in order, and the first matching rule determines the action taken. One of the most important capabilities of Cloud Armor is protection against common web attacks. It includes pre-configured rules designed to detect threats such as SQL injection, cross-site scripting, and other techniques commonly used to exploit web applications. These rules are built on industry standards and continuously updated to reflect new attack patterns. By enabling them, you gain a strong baseline defense without needing to manually design every rule from scratch. Cloud Armor also plays a critical role in defending against denial-of-service attacks. Large-scale traffic floods can overwhelm applications and make them unavailable to legitimate users. Because Cloud Armor is integrated with Google's global infrastructure, it can absorb and filter massive volumes of traffic at the edge of the network. Malicious requests are blocked close to their source, long before they can consume back-end resources. Another powerful feature of Cloud Armor is adaptive protection. Instead of relying only on static rules, adaptive protection analyzes traffic patterns over time. It learns what normal traffic looks like for your application and identifies sudden spikes or unusual behavior. When a potential attack is detected, Cloud Armor can automatically create rules to mitigate the threat, reducing the need for constant manual tuning. Cloud Armor integrates directly with Google Cloud Load Balancing. This means it protects applications running on Compute Engine, Google Kubernetes Engine, and other backend services that sit behind an HTTP or HTTPS load balancer. Once a security policy is attached to a load balancer, every incoming request is evaluated consistently, regardless of where the application is hosted. Configuring Cloud Armor is not just about blocking traffic. It is also about control and visibility. Logs generated by Cloud Armor provide insight into which requests were allowed or denied, and why. This visibility helps security teams understand attack patterns, validate rules, and fine-tune policies without blindly guessing. From a security design perspective, Cloud Armor supports the principle of limiting exposure at the perimeter. By stopping malicious traffic early, it reduces the likelihood that attackers will ever interact with your application code or backend systems. This containment significantly reduces risk and complements other security layers such as identity controls, application-level validation, and monitoring. In a well-architected cloud environment, Cloud Armor becomes a critical part of defense in depth. It does not replace secure coding practices or internal access controls, but it strengthens the outer boundary of your system. When configured thoughtfully, it ensures that only legitimate, well-formed requests are allowed through, while threats are stopped quietly and efficiently at the edge. Configuring Cloud DNS security settings. Cloud DNS often feels like a background service, quietly translating names into IP addresses, but from a security perspective, it sits directly on the network perimeter. Every request that enters your cloud environment usually begins with DNS. Because of this, configuring Cloud DNS security settings correctly is a critical part of controlling who can reach your services and how they discover them. At its core, Cloud DNS is responsible for answering one simple question. When someone asks for a domain name, where should that request be sent? If this process is not tightly controlled, attackers can exploit it to map your infrastructure, redirect traffic, or disrupt services. Securing DNS is about ensuring that only the right systems can ask questions, only trusted answers are returned, and changes to DNS records are carefully governed. One of the first security considerations is visibility. Public DNS zones expose records to the internet by design, which is necessary for public-facing applications. However, this also means that anything published there can be discovered by anyone. Security-aware DNS configuration starts by being intentional about what is public and what is not. Internal services, databases, and management endpoints should never rely on public DNS. Instead, they should be placed behind private DNS zones that are accessible only from within your virtual private cloud or from explicitly connected networks. Private DNS zones create a clear boundary. They allow internal resources to resolve names without ever exposing those names or IP addresses to the public internet. When configured correctly, this reduces reconnaissance opportunities for attackers and keeps sensitive service details hidden. It also simplifies internal architecture, because workloads can communicate using stable domain names rather than hard-coded IP addresses. Another important aspect of cloud DNS security is controlling who can modify DNS records. DNS changes are powerful. A single incorrect or malicious update can redirect traffic to an attacker-controlled system or take an application offline. For this reason, DNS administration should be tightly restricted using identity and access management. Only specific roles should be allowed to create, update, or delete DNS records, and these permissions should be limited to the minimum scope required. Read-only access can be granted more broadly for visibility, but write access must be carefully guarded. Logging and monitoring play a key role in protecting DNS. Cloud DNS integrates with logging services that record queries and changes. Query logging helps you understand how your domains are being used and can reveal unusual patterns, such as unexpected spikes in requests or queries coming from unfamiliar sources. Change logs provide an audit trail of who modified DNS records and when. In a security incident, these logs often become one of the first places investigators look to understand what happened. DNS is also a common target for abuse through denial-of-service attacks. Cloud DNS is designed to be highly available and resilient, but security configuration still matters. Using managed DNS reduces the risk compared to self-hosted DNS servers because the underlying infrastructure is protected against large-scale attacks. From a perimeter perspective, this shifts the burden of availability and attack resistance to the cloud provider, while you focus on correct configuration and access control. Another layer of protection involves integrating DNS with network segmentation. Different environments, such as development, testing, and production, should have separate DNS zones or clearly separated namespaces. This prevents accidental cross-environment access and limits the impact of mistakes. If a misconfiguration occurs in a development zone, it should not affect production traffic. This separation directly supports the principle of limiting the blast radius. DNS security is also closely tied to hybrid and multi-network setups. When on-premises networks or other clouds are connected to Google Cloud, DNS forwarding and peering must be configured carefully. Only required DNS queries should be forwarded, and trust boundaries must be clearly defined. Overly broad DNS sharing can unintentionally expose internal names or allow untrusted networks to resolve sensitive domains. In the end, configuring cloud DNS security settings is about treating DNS as a security control, not just a convenience service. By carefully choosing between public and private zones, restricting who can make changes, enabling logging, and aligning DNS with your network boundaries, you turn name resolution into a controlled gateway rather than an open directory. When DNS is secured at the perimeter, it quietly enforces structure, visibility, and trust across your entire cloud environment, often without users ever noticing it is there. Managing zones and records in cloud environments. Name resolution is one of those invisible foundations that everything else depends on. When applications know where to find each other, services work smoothly. When they do not, even a healthy system can appear broken. This is where managing DNS zones and records becomes critical. In Google Cloud, DNS is handled through Cloud DNS, a managed service that removes the need to operate your own DNS servers. At the heart of Cloud DNS is the concept of a managed zone. A managed zone is simply a container that holds all DNS records for a specific domain name. If your domain is example.com, the managed zone is the place where every record related to that domain is stored and controlled. When a managed zone is created, Google automatically assigns a set of authoritative name servers to it. These name servers are responsible for answering DNS queries for that domain, and they should not be manually changed because they are essential for correct resolution. Managed zones can be public or private, and the difference between them is fundamental to security and network design. A public zone contains DNS records that are visible to the entire internet. This is what you use for public websites, APIs, or services that must be reachable from anywhere. A private zone, on the other hand, is only visible inside specific virtual private cloud networks. These private zones are typically used for internal services, backend systems, or hybrid environments where cloud resources must resolve names that are not exposed publicly. Visibility for private zones is explicitly controlled by attaching them to one or more VPC networks, ensuring that only authorized networks can resolve those names. Beyond public and private zones, Cloud DNS also supports more advanced zone types. Forwarding zones allow you to override normal DNS resolution for specific domains and forward those queries to external DNS servers. This is commonly used in hybrid setups, where some domains are still managed on premises or by another DNS provider. Instead of trying to duplicate records, Cloud DNS simply forwards requests to the appropriate destination. Peering zones solve a different problem. When two VPC networks are connected, they do not automatically share DNS information. DNS peering allows one network to forward DNS queries to another network's Cloud DNS configuration, enabling controlled name resolution across environments without merging DNS ownership. Once zones are in place, the next responsibility is managing DNS records themselves. DNS records map names to information, such as IP addresses, mail servers, or aliases. Cloud DNS records are not changed casually or one at a time. Instead, changes are grouped into transactions. A transaction is a set of additions and removals that are applied together as a single atomic operation. This design ensures consistency. Either all changes succeed, or none of them do. The system is never left in a partially updated state, which is especially important when modifying critical records that applications rely on. The lifecycle of a record change follows a clear flow. First, a transaction is started for a specific managed zone. Then, records are added or removed within that transaction. Finally, the transaction is executed, at which point Cloud DNS validates the changes and propagates them. This approach provides safety, traceability, and predictability, especially in production environments. It also allows teams to review and validate planned changes before they go live. Time to live, commonly called TTL, plays an important role in record management. TTL defines how long DNS resolvers are allowed to cache a record before they must ask again. Short TTLs allow changes to propagate quickly but increase query volume. Longer TTLs reduce DNS traffic but slow down changes. Choosing the right TTL is a balance between flexibility and stability, and it often depends on how frequently a service changes and how critical rapid updates are. From a security perspective, managing zones and records is not just about availability. It is also about control. Cloud DNS integrates with identity and access management, allowing permissions to be applied at both the project level and the individual zone level. This makes it possible to separate responsibilities, for example, allowing one team to manage public DNS records while another manages private internal zones. This separation reduces risk and aligns with the principle of least privilege. When designed properly, DNS becomes a quiet but powerful enabler. Managed zones define clear boundaries for name resolution. Transactions ensure safe and predictable updates. Public, private, forwarding, and peering zones together support everything from simple websites to complex hybrid architectures. By treating DNS as a controlled, secure, and well-structured service, you ensure that every system in your environment can reliably find what it needs, exactly when it needs it. Topic: configuring boundary segmentation. In this section, we move beyond the outer perimeter and into the next layer of defense known as boundary segmentation. Boundary segmentation is about deliberately dividing your cloud environment into clearly defined trust zones so that access is controlled not just at the edge, but also between internal components. The goal is simple but critical. Even if an attacker or a misconfiguration gets past one layer, it should not automatically grant access to everything else. Think of a large enterprise building rather than a single open hall. The main entrance may have security, but once inside, sensitive areas like server rooms, finance offices, or executive floors are protected by additional doors, badges, and checkpoints. Boundary segmentation applies this same idea to cloud infrastructure. Each boundary represents a line of control where traffic, identities, and permissions are evaluated again. In Google Cloud, boundary segmentation is implemented primarily through networking constructs and organizational design choices. Virtual private cloud networks form the foundation. A VPC defines an isolated network boundary where resources can communicate privately. Within a VPC, subnets allow you to further divide workloads by function, environment, or sensitivity. For example, front-end services, back-end services, and databases can each live in separate subnets, even if they belong to the same application. Segmentation becomes more powerful when you consider how traffic flows between these boundaries. Firewall rules act as gatekeepers. They define exactly which sources are allowed to talk to which destinations, over which protocols and ports. By default, Google Cloud follows a deny-by-default mindset when you design your rules carefully. You explicitly allow only the traffic that is required for the application to function. Everything else is blocked. This sharply reduces the potential blast radius if something goes wrong. Boundary segmentation is not limited to a single VPC. In real-world environments, organizations often use multiple VPCs to isolate teams, applications, or environments such as development, testing, and production. VPC peering allows controlled connectivity between these networks. Peered VPCs can communicate using private IP addresses without sending traffic over the public internet. However, peering does not automatically mean full trust. Firewall rules in each VPC still apply, allowing you to precisely control what is reachable across that boundary. As environments grow larger, managing segmentation at scale becomes a challenge. This is where shared VPCs play a crucial role. A shared VPC allows an organization to centralize network administration in a host project, while individual teams deploy resources in separate service projects. The network team controls subnets, routing, and firewall policies, while application teams focus only on their workloads. This separation of duties is a key security principle and greatly reduces the risk of accidental overexposure. Boundary segmentation also extends beyond networking into service-level boundaries. VPC service controls introduce the concept of service perimeters. A service perimeter defines a logical boundary around Google-managed services, such as cloud storage, BigQuery, or Bigtable. Once a project is inside a service perimeter, access to those services is restricted so that data cannot be accessed or exfiltrated from outside the boundary, even by identities that would otherwise have valid permissions. This is especially important for protecting sensitive data against credential theft or misconfigured access. These service perimeters work together with access levels, which define the conditions under which requests are allowed to cross a boundary. Access levels can evaluate factors such as the source IP address, the identity making the request, or the security posture of the device. This ensures that access is not just about who you are, but also where you are coming from and under what conditions. When all these mechanisms are combined, boundary segmentation becomes a powerful strategy rather than a single feature. VPCs isolate networks. Subnets organize workloads. Firewall rules control traffic. VPC peering enables controlled connectivity. Shared VPCs enforce separation of duties. Service perimeters protect managed services and sensitive data. Each boundary adds another decision point, another checkpoint where trust must be proven. The key takeaway is that strong cloud security does not rely on a single wall. It relies on many carefully placed boundaries, each designed to limit movement, reduce exposure, and contain damage. By thoughtfully configuring boundary segmentation, you create an environment where failures are isolated, attacks are slowed, and sensitive assets remain protected even when something inevitably goes wrong. Topic: configuring security properties of a VPC network, VPC peering, shared VPC, and firewall rules. A virtual private cloud network, often called a VPC, is the foundation of networking in Google Cloud. It defines how resources communicate with each other, how traffic flows, and how access is controlled. Configuring the security properties of a VPC is not a one-time task. It is an ongoing design decision that directly affects how well your environment can resist attacks and contain failures. A VPC network provides logical isolation. Even though it runs on shared physical infrastructure, your VPC is separated from other customers by design. Within this network, you define IP address ranges, subnets, routing rules, and security controls. One of the most important security properties of a VPC is that it is global. This means a single VPC can span multiple regions, allowing resources in different locations to communicate securely over Google's private backbone instead of the public internet. Subnets divide a VPC into smaller regional segments. Each subnet has its own IP range and acts as a boundary for resources such as virtual machines and managed services. By carefully planning subnet ranges and keeping workloads separated by function or sensitivity, you reduce the risk that a compromise in one area spreads to others. This is a practical application of limiting the blast radius at the network level. Routing is another critical security aspect of a VPC. Routes determine how traffic leaves and enters subnets. By default, Google Cloud creates routes that allow resources to communicate internally. Custom routes can be added to control traffic flow more precisely, such as forcing traffic through security appliances or blocking unintended paths. Misconfigured routes can expose internal services, so they must be reviewed carefully as part of a secure design. VPC peering allows two separate VPC networks to communicate with each other using private IP addresses. This is commonly used when different teams, projects, or organizations need to share services while maintaining separate environments. Peering does not merge networks. Each VPC remains independent, with its own firewall rules and routing policies. This separation is important because it ensures that access is explicitly granted rather than implicitly shared. When configuring VPC peering, it is essential to understand that traffic flows only between the peered networks and only through private IP space. There is no transitive routing. If VPC A is peered with VPC B, and VPC B is peered with VPC C, VPC A cannot automatically reach VPC C. This design prevents unintended network access and helps maintain clear trust boundaries between environments. Shared VPC takes a different approach. Instead of connecting independent networks, shared VPC allows multiple projects to use a single, centrally managed VPC network. One project, called the host project, owns the VPC and defines its subnets and firewall rules. Other projects, known as service projects, attach their resources to that shared network. This model is especially useful in large organizations. The networking team can control IP addressing, routing, and security policies from the host project, while application teams deploy resources in their own service projects. This separation of responsibilities improves security by ensuring that network-level controls are managed consistently and not reconfigured independently by every team. Shared VPC also helps enforce organizational standards. For example, firewall rules that restrict internet access or require traffic inspection can be applied centrally. Application teams cannot bypass these controls, even if they have full administrative access within their own service projects. This reduces configuration drift and lowers the risk of accidental exposure. Firewall rules are one of the most visible and powerful security mechanisms in a VPC. They define what traffic is allowed or denied based on direction, protocol, port, source, destination, and target. In Google Cloud, firewall rules are stateful, meaning that if an incoming connection is allowed, the return traffic is automatically permitted. Firewall rules operate at the VPC level, but can be scoped to specific targets such as service accounts or network tags. This allows very precise control. Instead of allowing traffic to all virtual machines in a subnet, you can allow it only to workloads that perform a specific role. This approach aligns closely with the principle of least privilege. Ingress rules control incoming traffic to resources, while egress rules control outbound traffic. Many environments focus heavily on ingress rules and overlook egress. However, controlling outbound traffic is just as important. Restricting egress can prevent compromised systems from communicating with command and control servers or exfiltrating data. Firewall rules are evaluated based on priority. Lower-numbered priorities are evaluated first. If a rule matches, the action is taken and evaluation stops. This makes rule order critical. A broadly permissive rule with a higher priority number can accidentally override a more restrictive rule if not designed carefully. Regular audits of firewall rules help identify overly broad access and unused exceptions. By combining secure VPC configuration, carefully planned subnetting, controlled VPC peering, centrally managed shared VPCs, and well-designed firewall rules, you create a layered network security model. Each layer reinforces the others. Even if one control fails or is misconfigured, the remaining layers continue to protect the environment. This is how strong cloud network security is built, not through a single setting, but through deliberate design and continuous attention. Configuring VPC peering is a way to privately connect two virtual private cloud networks so that resources in one network can communicate directly with resources in the other. Once peering is configured, the networks behave as if they are part of the same internal environment, even though they remain separate and independently managed. Traffic between the peered networks stays on Google's internal network and does not traverse the public internet, which improves both security and performance. To understand why VPC peering is useful, imagine two teams within an organization. One team runs backend services such as databases and internal APIs, while another team runs application servers that need to access those services. Each team uses its own VPC network for isolation and control. Without VPC peering, communication between these networks would require external IP addresses, VPN tunnels, or load balancers. With VPC peering, the networks can communicate directly using private IP addresses, simplifying the architecture and reducing exposure. When configuring VPC peering, it is important to understand that the relationship is non-transitive. This means that if Network A is peered with Network B, and Network B is peered with Network C, Network A does not automatically gain access to Network C. Each peering connection is explicit and limited to the two networks involved. This design helps limit unintended access and supports the principle of least privilege. The configuration process itself involves creating a peering connection request from one VPC network to another, and then accepting that request on the peer network. Both networks must have unique, non-overlapping IP address ranges. Overlapping CIDR ranges are not allowed because the routing system would not be able to determine where traffic should be sent. Careful IP planning is therefore essential before setting up VPC peering, especially in large environments. Once the peering is active, routes are automatically exchanged between the networks. This allows resources in each VPC to discover how to reach the other network's IP ranges without manual route configuration. However, only subnet routes are exchanged by default. Custom routes, such as those pointing to on-premises networks through VPN or interconnect, are not automatically shared unless explicitly enabled. This behavior prevents accidental access to external networks and keeps connectivity tightly controlled. Security remains a shared responsibility even after peering is established. VPC peering itself does not bypass firewall rules. Each network continues to enforce its own firewall policies independently. For traffic to flow successfully, firewall rules must allow the required ingress and egress traffic on both sides. This means you can peer two networks while still strictly limiting which services and ports are accessible, further reducing the blast radius in case of a compromise. Another important aspect of VPC peering is that it does not support network address translation between peered networks. Traffic uses the original source and destination IP addresses. This makes logging, monitoring, and troubleshooting more transparent because the true identity of the communicating resources is preserved. At the same time, It reinforces the need for careful IP range design and clear firewall policies. VPC peering is commonly used for shared services architectures, where one central VPC hosts services like logging, monitoring, or authentication systems, and multiple application VPCs connect to it. It is also useful for connecting environments such as development, staging, and production, while keeping them logically separate. In all cases, the goal is to enable necessary communication without merging networks or sacrificing security boundaries. In summary, configuring VPC peering allows organizations to connect VPC networks in a secure, private, and scalable way. By keeping networks separate while enabling controlled communication, VPC peering supports strong security principles, simplifies network design, and helps ensure that access is granted only where it is truly needed. Topic: Creating a shared VPC and sharing subnets. When an organization grows in the cloud, a single project and a single network quickly become difficult to manage. Different teams need independence, but security teams still need centralized control. This is where the concept of a shared VPC becomes important. A shared VPC allows an organization to create and manage a virtual private cloud network in one central project, while allowing other projects to use that network securely. Instead of every team creating its own isolated VPC, networking is designed once and shared in a controlled way. This approach improves security, reduces duplication, and makes large environments easier to govern. The process begins with choosing a host project. The host project is the owner of the shared VPC. This is where the VPC network is created and managed. All core networking components live here, including subnets, routes, and firewall rules. The host project is typically controlled by a central platform or security team because any changes here affect all connected projects. Once the host project is identified, shared VPC is enabled on that project. Enabling shared VPC transforms the project into a central networking hub. From this point onward, its VPC networks can be shared with other projects in the same organization. The next step is selecting service projects. Service projects are the projects where workloads actually run. These might belong to application teams, data teams, or development environments. Instead of creating their own VPCs, these projects attach to the shared VPC hosted in the host project. After a service project is attached, it can use specific subnets from the shared VPC. Subnet sharing is deliberate and controlled. Not every subnet has to be shared with every service project. For example, a production application project may only be allowed to use production subnets, while a development project may be restricted to development subnets. This separation helps enforce environment boundaries and reduces the risk of accidental access. When a subnet is shared, resources created in the service project, such as virtual machines, managed instance groups, or GKE nodes, receive IP addresses from that shared subnet. Even though the compute resources live in different projects, they all communicate over the same underlying network. This makes connectivity simple and predictable while keeping project-level separation intact. Access control plays a critical role in shared VPC design. Permissions are carefully divided between networking administrators and service project users. Network administrators in the host project control the VPC, subnets, routes, and firewall rules. Users in service projects are typically allowed to create resources that attach to the shared subnets, but they are not allowed to modify the network itself. This separation of duties helps prevent misconfigurations and limits the blast radius of mistakes. Firewall rules are also centrally managed in the host project. These rules apply to traffic across the shared network, regardless of which project the resources belong to. By defining firewall rules once, security teams can enforce consistent policies across the entire organization. At the same time, rules can be designed to allow or restrict communication between different service projects, depending on security requirements. Shared VPC also simplifies auditing and monitoring. Since network configuration is centralized, it becomes easier to review changes, track access, and detect misconfigurations. Logs and flow data can be analyzed from a single perspective, instead of being scattered across many independent networks. From a security perspective, Shared VPC reduces risk by limiting who can change critical network settings. It also reduces sprawl, because teams no longer create separate VPCs with inconsistent rules. From an operational perspective, it improves efficiency, because networking is built once and reused many times. In essence, creating a shared VPC and sharing subnets is about balancing control and flexibility. The organization maintains strong, centralized security over the network, while individual teams retain the freedom to build and operate their workloads. This design is especially powerful in large environments, where consistency, visibility, and controlled access are essential for long-term security and scalability. Topic: Using a shared VPC, imagine an organization that has many teams, many projects, and many applications running in Google Cloud. Each team needs freedom to build and operate their workloads, but the security team still needs control over the network. This is exactly the problem that shared VPC is designed to solve. A shared VPC allows you to create a single, centrally managed VPC network and share it across multiple projects. Instead of every project creating its own isolated network, one project becomes the host project. This host project owns the VPC network, including subnets, routes, and firewall rules. Other projects, called service projects, attach to this shared network and use it to run their workloads. From the outside, workloads in service projects behave as if they are part of the same network. Virtual machines, GKE clusters, and other resources can communicate across project boundaries using internal IP addresses. But behind the scenes, ownership is clearly separated. The network is controlled by the host project, while applications and resources live in the service projects. This separation is powerful from a security perspective. Network administrators manage the VPC, subnets, and firewall rules in one place. Application teams do not need permission to create or modify networks. They only get access to deploy resources into specific shared subnets. This reduces the risk of misconfiguration and prevents teams from accidentally weakening network security. Firewall rules in a shared VPC are also centrally enforced. Because firewall rules belong to the host project, security teams can define consistent rules that apply to all attached service projects. For example, they can restrict inbound access, control which services can talk to databases, and enforce segmentation between environments such as development and production. Even if a service project is compromised, the attacker cannot change the firewall rules unless they also have permissions in the host project. Shared VPC also supports the principle of least privilege. Teams only receive the permissions they need. A developer might be allowed to create virtual machines in a specific subnet, but not allowed to create new subnets or open firewall ports. This limits the blast radius of mistakes and reduces the impact of compromised credentials. Another key benefit is scalability. Large organizations often have hundreds of projects. Managing separate networks for each project becomes complex and error-prone. With shared VPC, network architecture is defined once and reused everywhere. This makes it easier to apply compliance requirements, audit network access, and maintain a consistent security posture across the entire organization. Shared VPC works especially well with other Google Cloud services. Kubernetes clusters can use shared subnets. Private Google access can be enforced centrally. Network monitoring and logging are unified, making it easier to detect suspicious activity and respond to incidents. In simple terms, shared VPC lets you centralize control without slowing teams down. Security teams define and protect the network. Application teams focus on building and running workloads. The result is a cloud environment that is easier to manage, harder to misuse, and far more secure by design. Topic: Configuring network isolation and data encapsulation for N-tier application. Design in a modern cloud environment, applications are rarely built as a single unit. Most real-world systems follow an N-tier design, where different parts of the application are separated into layers such as the web tier, application tier, and database tier. Each tier has a specific responsibility, and each one must be protected differently. Configuring network isolation and data encapsulation is the foundation that keeps these tiers secure, controlled, and predictable. At the center of this design is the virtual private cloud network. A VPC provides a logically isolated network space inside Google Cloud where your resources communicate with each other. Even though everything runs on shared physical infrastructure, the VPC makes it feel like a private data center that only you control. This isolation is the first security boundary. Resources inside one VPC are not automatically visible or reachable from another VPC unless you explicitly allow it. In an N-tier application, network isolation starts by placing different tiers into separate subnets. For example, the web tier might live in a subnet that allows limited inbound access from the internet, while the application tier resides in a private subnet with no direct internet exposure. The database tier is usually placed in the most restricted subnet, accessible only from the application tier. By separating tiers at the network level, you reduce the chance that a compromise in one layer can spread to others. Data encapsulation plays an equally important role. When traffic flows between tiers, it should travel only through defined network paths and controlled interfaces. Inside a VPC, communication happens over Google's private backbone, not the public internet. This ensures that data moving between tiers stays within Google's secure network and is protected from external interception. Encapsulation ensures that each packet of data is wrapped within the boundaries of the VPC, maintaining confidentiality and integrity. As applications grow, a single VPC is often not enough. Different teams or environments such as development, testing, and production may need their own networks. This is where VPC peering becomes important. VPC peering allows two VPC networks to communicate with each other using private IP addresses without exposing traffic to the public internet. From a security perspective, peering is a controlled bridge. Networks remain separate, but selected resources can talk to each other as if they were part of the same network. In an N-tier design, VPC peering is often used to separate shared services from application workloads. For example, a central services VPC might host logging, monitoring, or authentication systems, while application tiers live in their own VPCs. Peering allows applications to securely consume these shared services without collapsing all workloads into a single network. Importantly, peering is not transitive. If VPC A is peered with VPC B, and VPC B is peered with VPC C, VPC A does not automatically gain access to VPC C. This limitation helps prevent accidental overexposure and keeps the blast radius small. For organizations with many projects and teams, shared VPC takes network isolation a step further. Shared VPC allows a central host project to own and manage the VPC network, while service projects attach their resources to that network. This model separates responsibilities. The networking team controls subnets, routes, and core security settings, while application teams deploy workloads without needing full network privileges. In an N-tier application, shared VPC enables consistent network design across multiple projects. Web, application, and database tiers can exist in different service projects, but still follow the same network security rules. This consistency reduces configuration errors and enforces standardized isolation patterns. It also prevents application teams from making risky network changes that could impact other tiers or environments. Firewall rules are the final and most precise control in network isolation. They define exactly which traffic is allowed or denied between resources. In a well-designed N-tier architecture, firewall rules are restrictive by default. Only the required communication paths are opened. The web tier may accept inbound traffic on specific ports, the application tier may accept traffic only from the web tier, and the database tier may accept traffic only from the application tier. Firewall rules work at the VPC level and apply to resources based on network tags or service accounts. This allows security controls to follow the workload rather than relying on static IP addresses. When combined with isolation through subnets, peering, and shared VPC, firewall rules act as precise gates between tiers. Even if a resource is compromised, firewall restrictions limit what it can reach next. When all these elements come together, the result is a secure and resilient N-tier design. Network isolation ensures that each tier is separated and protected. Data encapsulation keeps traffic private and contained within trusted boundaries. VPC peering enables controlled communication between networks without sacrificing isolation. Shared VPC enforces centralized governance while supporting scale. Firewall rules provide fine-grained control over every connection. Together, these mechanisms transform the network from a simple connectivity layer into a powerful security control. Instead of relying on trust, each tier communicates only because it is explicitly allowed to do so. This approach significantly reduces risk, limits the impact of failures or attacks, and forms a strong foundation for secure cloud application design. Configuring VPC service controls in a modern cloud environment. Not all security risks come from the internet. Some of the most damaging incidents happen when sensitive data is accessed from inside the cloud itself. This is where VPC service controls play a critical role. They are designed to protect your most valuable data and services by creating strong security boundaries around them. VPC service controls work by defining a secure perimeter around specific Google Cloud services, such as BigQuery, Cloud Storage, or Bigtable. Once a service is placed inside this perimeter, access to it is tightly controlled. Even if a user or service account has valid credentials and permissions, access can still be denied if the request comes from outside the trusted boundary. This adds a powerful layer of protection beyond traditional identity and access management. To understand this clearly, imagine your cloud services are located inside a secure research facility. Having an ID badge alone is not enough to enter. You must also be inside the building's physical boundary. VPC service controls enforce a similar concept in the cloud. They ensure that sensitive services can only be accessed from approved networks, projects, or environments. One of the main threats VPC service controls are designed to prevent is data exfiltration. This occurs when data is copied or moved out of your environment, either accidentally or maliciously. For example, if an attacker compromises a service account and tries to download sensitive data to an external location, VPC service controls can block that request, even though the credentials appear valid. The data remains protected because the request violates the defined security perimeter. These controls are especially important in environments where multiple projects and teams operate together. In large organizations, it is common to have shared services, analytics platforms, or centralized data lakes. VPC service controls allow you to protect these shared resources by ensuring that only approved projects and networks can communicate with them. This reduces the risk that a mistake or breach in one project can impact sensitive data in another. VPC service controls also integrate closely with VPC networks and firewall rules. While firewall rules control network-level traffic, such as which IP ranges can communicate, VPC service controls operate at the service level. They focus on protecting managed Google Cloud services, not just virtual machines. Together, these layers create a stronger defense by controlling both how traffic flows and where sensitive services can be accessed from. Another important feature is the ability to define access levels. Access levels specify the conditions under which a request is allowed, such as originating IP ranges, device security status, or user identity attributes. By combining access levels with service perimeters, you can enforce very precise security policies that match your organization's risk tolerance. In shared environments, such as those using shared VPC service controls become even more valuable. Multiple projects may use the same network, but not all of them should have access to the same sensitive services. Service perimeters allow you to clearly separate which projects are trusted and which services they are allowed to reach, without redesigning your entire network architecture. Ultimately, VPC service controls are about assuming that credentials alone are not enough to guarantee security. They recognize that breaches happen and mistakes occur. By placing strong boundaries around critical services, they limit how far an incident can spread and how much damage it can cause. This approach aligns directly with the principle of limiting the blast radius and is a key component of a mature, defense-in-depth cloud security strategy. Establishing private connectivity in a cloud environment. Not every system should be exposed to the public internet. In fact, Some of the most important communication in Google Cloud happens quietly, behind the scenes, over private paths that never touch the outside world. This is where establishing private connectivity becomes essential. Private connectivity is about allowing resources to communicate securely and efficiently without relying on public IP addresses. Instead of sending traffic out to the internet and back in again, systems talk directly to each other over Google's internal network. This reduces exposure, lowers latency, and gives you far more control over who can talk to what. Inside a VPC network, private connectivity begins with internal IP addressing. Every VM, service, or internal load balancer can communicate using private IPs that are reachable only within the network, or across networks that you explicitly connect. By default, these internal addresses are isolated. Nothing outside the VPC can reach them unless you deliberately allow it. When workloads need to communicate across different VPC networks, VPC peering becomes a powerful option. Peering creates a private, one-to-one connection between networks, allowing them to route traffic to each other using internal IP addresses. There is no public internet involved, no gateways, and no VPN tunnels to manage. Traffic stays on Google's backbone, which improves performance and reduces the attack surface. At the same time, peered networks remain separate. They do not automatically share firewall rules or IAM policies, which helps preserve isolation. Shared VPC takes private connectivity a step further by allowing multiple projects to use a single, centrally managed VPC network. In this model, the network lives in a host project, while workloads run in service projects. Resources in different projects can communicate privately as if they were in the same network. This approach is especially useful in large org.